2. But now our millimoles of base is 20 times 0.100, so it's also 2. This is the equivalency point. pH then is going to equal 7. Okay? Once I know I'm at the equivalency point, strong acid, strong base, I go immediately to 7 as the pH. Now, let's add 25 milliliters of base. So now our millimoles of base is 25 milliliters times 0.100. So that's 2.50 millimoles. Okay, so now we're post equivalency point because millimoles of base is greater than millimoles of acid. So our excess base is just going to be 2.50 minus 2, 0.50. And the molarity of the base is just going to be 0.50 divided by the new volume, 45 milliliters. So 0.5 divided by 45, its concentration is 0.011 molar. So our POH is 1.96. So our pH is 12.07. I mean, it's 12.04. Okay? So there are the points in a strong acid, strong base titration curve. And we've worked all the way through an example. Now, let's talk about a weak acid, strong base titration curve. Now again, we've got the initial point, the pre-equivalency point, the equivalency point, and the post-equivalency point. We're going to have a little bit of change to our concentration because we're dealing with a weak acid now instead of a strong acid. So at the initial point, 0 milliliters of base have been added. All we have is a weak acid solution. So you need Ka to find the hydronium ion concentration. If the Ka is small enough until you're going to make the assumption, we can kind of do a quickie. Okay, we're going to take a shortcut. When we make the assumption, all the math that we do comes down to the hydronium ion concentration is equal to Ka times the acid initial concentration, all raised to the square root. Well, all raised to the 1/2 power, that's the square root. pH equals the negative log then of hydronium ion concentration. Pre-equivalency point, millimoles of acid initially is millimoles greater than millimoles of base added. We're in the buffer region. The millimoles of weak acid is going to be molarity of the acid times volume in acid initially. Millimoles of base made is the molarity of the strong base times the volume of the strong base added. Unreacted millimoles of acid. What's going to be left is millimoles of acid initially minus millimoles of base added. And then we use the Henderson-Hasselbalch equation. Okay? we're going to say pH equals pKa plus the log of millimoles of base divided by millimoles of acid. Sorry guys, got a little carried away there. Now, at the equivalency point, we cannot automatically say for a weak acid, strong base titration that the pH is 7. Because at this point, all of the weak acid has been converted to conjugate weak base, and what we now have is a weak base solution. And we have the reaction, the anion weak base plus water going to conjugate weak acid and the hydroxide ion. This conjugate weak acid is a newly minted acid molecule, okay? Not one of the originals. So the molarity of the weak base is just the millimoles of weak base added divided by the new volume of the solution, okay? And Kb for that weak acid is Kw divided by Ka, 1.00 times 10 to the minus 14 divided by Ka. And making assumptions, the hydroxide ion concentration is just going to equal the molarity of the weak base times Kb all raised to the 1/2 power. The hydroxide ion concentration is just the negative log of hydroxide ion. And pH is going to be 14 minus POH. Post-equivalency point, your pH depends on your excess strong base. So millimoles of excess strong base is going to be millimoles of base added minus millimoles of acid initially, which gives us the molarity of our excess base is millimoles of excess base divided by the new volume. And pH is just going to equal the negative log of hydroxide ion concentration, which is the negative log of the strong base in excess. And pH is going to be 14 minus POH. Okay? So now it's time to do an example problem. All right? And when we do this example problem, we'll be done with our acids and bases, and we'll start talking about slightly soluble salts.